So let's start. So Pascal's triangle is this structure that looks a little like this. Okay? We start with the 1 on top, and then 2 more 1s. There's always 1s on the edge. And how we generate new numbers is we take 2 adjacent numbers in a row, and their sum is the number directly below it. So here in the second row, by convention, this is called the 0th row. This is the first row, and this is the second row, right? To get the remaining element of the second row, I would add this one and this one to get 2. Okay? You know what? Why don't I move this closer to the middle, right? To get the third row, I'd have 1s on the end, and then my next number after the 1 would be the sum of 1 and 2, which is 3, right? So I have a 3 down here, because 1 plus 2 is 3. Then what's the number that comes after it? Another 3, right? Because 2 plus 1 is 3 again. And then I have a 1. Okay? The fourth row, I keep following this process. 1, 4, 6, 4, 1. The fifth row, 1, 5, 10, 10, 5, 1, and so on and so forth. We keep using this process, and the thing we notice is that if you take 2 adjacent numbers, so for example 6 and 4, the way this triangle is generated is by taking adjacent numbers and having the number directly below them be their sum. So 6 plus 4 is 10. Okay? So what are some patterns you notice here in Pascal's triangle? It could be very basic, it could be something a little more intricate, anything. Yeah.
As we go along the second diagonal, it just goes 2, 3, 4, 5. Or 1, 2, 3, 4, 5.
Good. So one pattern is second diagonal gives us 1, 2, 3, 4, 5, 6, so on and so forth, right? A 6 would come here, a 7 would go there, 8, so on and so forth. So good, that's one pattern. What's another pattern? How many elements are in each row? Right? And notice I called it the 0th row for a reason, because the second element in the nth row is n. Otherwise, if I started with the first row, it would be off by a factor, by 1. Right? So I started counting with the 0th row so that the 4th row has 4 in it, the 5th row has 5 in it, and so on and so forth. What were you going to say?
The row indexes I choose J if I is the row and J is the index. Okay,
so we'll get to that in just a sec. What are some other patterns that don't revolve around choosing that we can just get from looking at this? How many numbers are in the nth row? N plus 1 numbers in the nth row. What do you notice about individual rows? What's one property of them? Symmetric. Each row is symmetric? Anything else? Okay, there are also some more involved properties. Let me write out another row for that. So the 6th row, 15, get rid of this, 20, 15, 6, and 1, right? This one's called the hockey stick theorem. How many people have seen that before? The hockey stick theorem? Okay, so what that says is, if I make this shape that looks like a hockey stick, the 3 numbers that are on the stem add to the last number. So 1 plus 4 plus 10 gives you 15. Is that sort of clear? And that works for any row as long as you start from the top left column. So I could even do that here, right? 1, 1, 1, 1, that gives me 4. Right? 1, 2, 3, that gives me 6. So that's called the hockey stick theorem, and that's something we can formalize using algebra in just a bit. Are there any others? There's one in particular that I want to see if someone notices. I didn't know it until today when I was preparing for this. So it's really sort of hidden. Okay, so this last one that I'm getting at is if we look at numbers in the second diagonal, so that's the diagonal right here, that reads 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth. There's an easy way to calculate that number squared. So for example, 5 squared happens to be the number immediately to the right of 5 and the number below both, 10 plus 15. Okay? 2 squared, for example, is the number immediately to the right of 2 and the number below both of them, so 2 squared is 1 plus 3, and so on and so forth. Does everyone see that as well? So any questions with the basic premise of what Pascal's triangle is and some of these patterns that we just identified? Okay, so the next sort of step in our journey with Pascal's triangle is identifying that these numbers are all numbers we've seen before, right? And it turns out you can write the triangle like this. 0, choose 0, 1, choose 0, 1, choose 1, 2, choose 0, 2, choose 1, 2, choose 2, and so on and so forth. Is that clear? So before here, we never introduced the idea of, choosing or factorial. We sort of just drew the structure. We start off with 3 ones at the top and then generate successive numbers by adding adjacent numbers and putting that number below them. But it turns out these numbers are exactly the combinatorial terms that we saw before, right? So how do I get the nth row of Pascal's triangle? Well, that's just n choose 0, n choose 1, so on and so forth. How do I get the element at the nth row and kth column? Oops. N choose k. Right? And so here, all of our indexing is 0 indexing, right? So we have a 0th row and 0th column, right? So for example, this number right here is the 4th row and 2nd column, but that's when we 0 index both the rows and columns. So any questions with this structure as well? Okay? And so the nice thing with having like a formula for each element in Pascal's triangle is that it allows us to quantify each of these patterns that we saw in terms of algebra, right? As opposed to just having to draw this tree. So one thing we noticed was that the numbers in the second diagonal correspond to 1, 2, 3, 4, 5, 6, so on and so forth, right? But notice the numbers in the second diagonal is just row number choose 1. Is that clear? Right here, the first diagonal is row choose 0, second diagonal is row choose 1, and so on and so forth. Right, so it might even make more sense to 0 index the diagonals as well. 0th diagonal is row number choose 0, first diagonal is row number choose 1, and so on and so forth. Is that clear? Right. And when we put it like that, it makes sense that the first or second diagonal, whichever way you want to index it, gives you 1, 2, 3, 4, 5, 6, 7, 8. Because we identified before that 1 choose 1, 2 choose 1, 3 choose 1, and so on and so forth is the same as 1, 2, 3. ... And so what we will do, both in this lecture and part of your homework that will come out tomorrow, is figure out ways to put in algebra some of the patterns we see in this structure of numbers. Any questions with what we've talked about so far? No? Okay, cool. So now I want to introduce this idea of combinatorial proofs formally. Okay? So instead of proving some statement algebraically, we can prove statements combinatorially by showing that both sides of the equal sign count the same quantity. Okay? So for example, recall what we did in discussion on Monday. We showed that the sum n choose 0, n choose 1, n choose 2, all the way until n choose n gives you 2 to the n. Okay, and I wanted to repeat that again here because I think it's pretty important. Right? And this way it's in the slides and also in the video. Okay? So to do a combinatorial proof of this fact right here, we need to show the left-hand side and the right-hand side both count the same thing. Right? They both count the number of ways to do this one thing. And since there's only one number of ways, like the number of ways to do anything is fixed, right? No matter how we count that, we should get the same number, right? So the left-hand side, we want to count the number of subsets of a set of size n, right? And we did this example before. Suppose we have our set being 1, 2, and 3. We could either, when we're creating a subset of it, it could include 0 elements, or 1 element, so just the numbers on their own, 1 as a set, 2 as a set, and 3 as a set. It could also include 2 elements, right? 1 and 2 as a set, or 2 and 3 as a set, or 1 and 3 as a set, or 3 elements, right? All 3 of them together, right? So in that case, the number of subsets should be 3 choose 0, plus 3 choose 1, plus 3 choose 2, plus 3 choose 3. But in the general case, if we have n elements, right, we're either going to choose 0, or 1, or 2, so on and so forth, until n, right? And for each of those cases, if we're choosing k elements, there's n choose k ways to do that. So then that gives us our sum, n choose 0, plus n choose 1, plus n choose 2, dot, 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 all the way until n choose n. For the right-hand side, again, the argument is for each of these n elements, there are 2 choices. Either it's included in our subset, or it's not included in our subset. Right? And this is the same argument as when we talked about counting the number of factors that a number has. Right? We take the exponent in the prime factorization, each of the exponents, add 1 to them, and multiply them all together. Because the exponents plus 1 tell us how many options there are for each prime base, right? And the whole point of multiplying when we're counting is multiplying the number of options at each step. And here, for the first element, there's 2 options. Either it's included in our subset or not included. For the second element, there's again 2 options. Included in our subset or not included. Since there's n elements, we're taking a product of 2 n times, which gives us 2 to the n. Okay? So this shows us that n choose 0, the sum from n choose 0 to n choose n, and 2 to the n must be the same number, because they're both counting the same thing, which is the number of subsets of a set with n elements. So that's the general premise behind a combinatorial proof. Okay, we didn't really do anything algebraic. We just reasoned about why these 2 quantities have to be the same. Any questions with this idea? Okay, let's look at another example, okay? Suppose we want to prove that m plus n choose 2 is equal to m choose 2 plus n choose 2 plus m times n, okay? So what we need to do is give some sort of argument as to why the left-hand side and the right-hand side both count the same quantity, okay? So suppose we have m Warriors fans and n Lakers fans, okay? The left-hand side is the number of ways we can just select 2 of these fans, right? In total, we have m plus n total fans, and we want to choose 2 of them, giving us m plus n choose 2. Any questions with the left-hand side? Okay? And now the right-hand side, we need to show that it counts the same thing. Well, so if we want to choose 2 basketball fans, right, and we have some group of m Warriors fans and n Lakers fans, there are 3 cases, right? Either we choose 2 Warriors fans, or 2 Lakers fans, or one of each. Is that clear? Right, since we have a pool of m plus n of them in total, we're going to choose either 2 from one group, 2 from another, or 1 from each. Any questions with that? Okay, and how many ways can we choose 2 Lakers fans? Well, there's m in total, we're choosing 2 of them, so we have m choose 2. We have 2 Lakers fans. We have n Lakers fans, and we're choosing 2 of them. That gives us n choose 2. And lastly, our case is 1 Warriors fan and 1 Lakers fan. Right, that's m choose 1 times n choose 1, which gives you m times n. And so since it's or in each of these 3 cases, we add them, right, giving us m plus m choose 2 plus n choose 2 plus m times n, which has to be equal to m plus n choose 2. So any questions with this example? So we reasoned about why both the left-hand side and right-hand side have to count the same thing. In this case, they're both counting the number of ways you can select 2 basketball fans from a group of m Warriors fans and n Lakers fans. Sound good? Okay. So here's another example of a combinatorial proof, right? This is Pascal's identity. Okay, it says that n choose k plus n choose k plus 1 is equal to n plus 1 choose k plus 1. Okay? So this might seem like it comes out of nowhere, but it's actually just a formalization of the fact that in Pascal's triangle, when you add 2 consecutive numbers, their sum is the number directly below them. Right? So if you want to look at that in action, that is exactly displayed here. Right? So for example, 3 choose 1 plus 3 choose 2, they sum to give us 4 choose 2. In this case, n is equal to 3 and k is equal to 1. Right? Another example, let's just say here n is 1 and k is 0. Now these 2 consecutive numbers add to give me the number immediately below them. Right? And maybe it's a little more evident here where you can actually see the numbers, but these 2 representations of Pascal's triangle are the same. Right? So any questions with where that comes from? Okay? So our rule is that n choose k plus n choose k plus 1 is equal to n plus 1 choose k plus 1. So I'll give you a couple minutes to discuss amongst yourselves. Try and come up with a combinatorial proof for this. Okay? I believe the algebraic proof for this was in this week's homework, right? Okay? So try and think of a combinatorial proof for this. Okay? So again, we're trying to come up with a combinatorial proof, i.e. one that doesn't involve algebra, rather one that gives an argument as to why both the left-hand side and right-hand side count the same quantities. Any questions with that? Okay, so just a quick recap. This is what the algebraic proof looks like. It's only a couple lines, but it's relatively messy, right? What you do, you expand them out in terms of what the expansion of n choose k means. Then you bring them to a common denominator, right? To bring this to a common denominator, you multiply this one by k plus 1 over k plus 1. And you multiply this one by n minus k over n minus k. Bring them into a common denominator, do some simplification, and you end up with this result, which is the same as n plus 1 choose k plus 1. So you can do it, but it's a little ugly, right? So now let's just look at the combinatorial proof for this, right? So the right-hand side pretty explicitly tells you the number of ways to choose k plus 1 people from a group of n plus 1, right? N plus 1 total, we want to choose k plus 1 of them, right? That's what the right-hand side tells us. Now, the left-hand side, we want to reason as to why it counts the same thing. Okay? We have n plus 1 people. Suppose they're numbered p1, p through, all the way through p n plus 1. Okay? So let's consider the very first person, P1. Okay? When we're picking our subset of k plus 1 people, there are two options, right? Either P1 is included or they are not included. Is that clear? Either this first person is in our subset of k plus 1 people or they are not in our subset of k plus 1 people, right? So there's two cases. If we include them, which we can do one choose one way, so that's why I didn't write one choose one, there are n people remaining, and we need to choose k of them, right? Because there's n plus 1 total, we chose one of them, and we need to choose k plus 1 people total, right? We already chose one person, so we need to choose k more. So that there's n choose k ways to do that. If we don't include person 1 in our group, there are still n people remaining, but we still need to choose k plus 1 people, right? Because our goal is to choose k plus 1 people in total. In the first case, we're including person 1 in our subset, so there are only k remaining. But in the second case, we're not including person 1 in our subset, so we still have k plus 1 people that we need to choose. Is that clear? So if, for example, if we just had 5 people, P1, P2, P3, P4, and P5, right? For example, the number of ways to choose, of these 5 people, choose 3 of them is 5 choose 3, right? Now, consider the first person. If we include them in our subset of 3 people, how many people are remaining? 4. And how many do we still need to choose? 2, right? Because we've already counted one of our 3 people. If we don't include this person, person 1, we still have 4 people remaining, but now we need to take 3 of them, because person 1 is not included in our subset. Right? So that's exactly what this combinatorial proof is saying. Right? We have these two cases, either this first person is included in our subset or not included in our subset. Right? And if we include them, we only have to multiply by 1 choose 1, which is why you don't see these 1 choose 1 and 1 choose 0 terms written there. Right? So therefore, the total number of ways to choose k plus 1 people from a group of n plus 1 is n choose k plus n choose k plus 1. Right? So that's what we've shown the left-hand side is. And we've already shown the right-hand side also counts the same thing. So these expressions have to be the same. Yeah?
Can you explain again why it was 4 choose 3?
Sure. So suppose our goal again is that we have 5 people and we want to choose 3 of them. There's 2 cases. The first case is we include person 1, and case 2 is we don't include person 1. Okay? In the first case, if we include person 1, our subset for sure will look like person 1 blank blank. Is that clear? There's 2 blanks we need to fill, and there's only 4 other people total, so it's 4 choose 2. In the second case, we're not including person 1, so we can remove that. So now we have 3 blanks, but still we only have 4 people possible to fill those blanks. So you have 4 total, choose 3. And that's exactly what we did in the general case, to show that it's n choose k plus n choose k plus 1. Any other questions with this argument? It does seem kind of foreign if you're not used to this idea of reasoning about why multiple things are the same, as opposed to doing it algebraically. Any questions? Yeah. Okay. Anything else? Okay. So I want you to try an example on your own. So give a combinatorial proof for Vandermon's identity, which states that m plus n choose r is equal to the sum of k going from 0 to r of m choose k times n choose r minus k. So let's stick with the example that we have m Warriors fans and n Lakers fans, okay? So our left-hand side is the number of ways we can choose r of them, right? And our right-hand side, this is the reasoning that we use. Right? Suppose we want to choose r basketball fans. If we choose 0 Warriors fans, we need to choose R Lakers fans. If we choose 1 Warriors fan, we need to choose R minus 1 Lakers fans, right? So whatever number of Warriors fans we choose, we need to choose R minus that number Lakers fans. Is that clear? Right? Either it's 0 and R, or 1 and R minus 1, or 2 and R minus 2, and so on and so forth, going all the way until R and 0. Is that clear? Right? And so, since it's or in each of these cases, right, these are all different possible cases, either we have M choose 0 times N choose R, or M choose 1 times N choose R minus 1, or, dot, 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 we follow that pattern, which gives us the right-hand side. So, on the left-hand side, it's more general. It's just saying we have M plus N people in total. How many ways can we choose R? On the right-hand side, it's breaking it down into cases. We'll choose, 0 and R, or 1 and R minus 1, and so on and so forth. And we multiply in each of these cases because, for example, in this case right here, if we choose 1 Warriors fan, in that same situation, we also have to choose R minus 1 Lakers fan. So we multiply in those cases, but together we add them all. Is that clear? Okay? And a neat little side effect of that is this identity. If you let M be equal to N and R also be equal to N, you get this identity. That the sum of the squares of a row of Pascal's triangle is 2n choose n. Is that clear? So here you let M be equal to R be equal to N. Okay? And so the first thing you might be saying is, well, in that case, if I let M and R both be N, the left-hand side will give me 2n choose N, which is fine. But the right-hand side will give me some k's going from 0 to n, n choose k, n choose n minus k. But that's not the same thing as this box down here. So why am I claiming these two things to be equal? Why am I claiming both of these to be equal? Exactly. This second term in both cases, right? So down here we can write it as n choose k times n choose k. And here we have n choose k times n choose n minus k. Remember that n choose k and n choose n minus k are both the same thing.